Welcome, grade 10s. We are going to focus on using tree diagrams and two-way tables to make calculations in probability. These two methods will help us to find the total number of possible outcomes when finding the probability of an event happening. Let's join Laura as she shows us how to use tree diagrams to do this.
We're going to be looking at tree diagrams next. This is probably people's worst nightmares, but actually you're going to see that they actually aren't that bad. Generally, for those of you that were a little bit unsure, you have a diagram that looks something like this, and basically it's a way of showing all your different possible outcomes. So for example, if I tossed a coin, I could have a head and a tail, and if I tossed it again, my options would be a head and a tail again. And obviously if I got a head first, I could get another head, or I could have got a head and a tail, and the second time I threw it, I could have got a first have had a tail, and then the next time had a head. So these are all my different possible answers. I could have got a head and a head, head and a tail and a head, or a tail and a tail. And you can see then that I've got 4 outcomes. Okay, so that's actually a very clear way of actually building up a table in order to find out what are my possible things that could actually happen. And this is very useful in some scenarios where, for example, they do affect each other. They're not independent events. For example, if I'm pulling marbles out of a bag and the number is dropping. So it's easy then to see what is my probability of something happening when I've done certain activities. But we're not going to go on to those harder examples just yet. So let's look at some basics. Right, let's look at example 4. A couple has 2 children. Use a tree diagram to calculate the probability that both children are girls and that the couple has a boy and a girl. Okay, so they say use a tree diagram, but there's no tree diagram here, so that means that it's up to you to actually draw that tree diagram. So let's have a look. What are we going to do first? We need to decide what are our different options. Now, if I have a child, the options are either they're going to be a boy or a girl. So my first child is either going to be a boy or a girl. Okay, now the probability, generally speaking, is I've got half a chance of getting a boy and half a chance of getting a girl. The second child, I still have the same choices. I've still got the chance of getting a boy or a girl, and a boy and a girl. Okay, you will always notice that the second choice is the same and it's duplicated for the second chances. So therefore, the first child, you've just got 1 branch split into 2, and the next time you've got 2 branches that are split into 2, because each of those children then will have 1 option each. So therefore, I can get a boy and a boy and a girl and a boy, or a girl and a girl. Those are my possibilities if I've got 2 children. Obviously, if I had 3 children, I'd have a lot more different possible combinations. But we're just focusing with 2 children at the moment. So it says, what are the possibility of both children are girls? Okay, now I have got half a chance here, and another half a chance there, another half a chance there, another half a chance there. And remember that each of these branches has to add up to a whole. So this section, these 2 add up to a whole, that section, those two have to add up to a whole, and this section, these two have to add up to a whole. So therefore you can actually see that you've actually got all the people that you need to consider, or all the options you need to consider. Now I want the combination of girl and girl. And again, remember the AND rule, that if I want something and something else, I need to multiply my two probabilities. I know the probability of getting girl the first time was half, and I know the probability of getting girl the second time is also half. So the probability of getting a girl and a girl is equal to the probability of a girl times the probability of a girl. And you can see that that's going to be a half times a half, which is equal to a quarter. Okay. What you do need to remember is that when you go along the branches, you need to multiply, and that is the most important rule, is that when I want to find out what are the chances of getting a girl and a girl, I need to go from this one to that one and times the probabilities. Right, let's move down a little bit. Right, the couple has a boy and a girl. Okay, now I could have quite a few different versions of a boy and a girl. Well, actually I could have a boy and then a girl. Or I could have a girl and a boy. So it doesn't say what order, they just said a boy and a girl. So what are the chances? You can see that there are 4 possible outcomes, and of those 4 possible outcomes, 2 satisfy these criteria. So I can have a boy and a girl going like this, or a girl and a boy doing like that. And you can see that because we worked out that to have 2 girls is a quarter, you'll see that all of these have got a quarter of a chance. And to get a boy and a girl and a boy will be a quarter plus a quarter. Note, it's plus and not multiply. Okay, because once I've gone along my branches, I need to remember that if I've got more than one combination that satisfies that option, I need to then add those possibilities. So I want to add a quarter and a quarter, and a quarter and a quarter is 2 quarters, which can be simplified to be a half. And you can see you have got half a chance. 2 out of the 4 options are a boy and a girl. The order might be different, so I might have had a boy first and then a girl second, or I could have had a girl first and then a boy second.
The next method we will look at is using a two-way table, which is also known as a contingency table. Let's go back to studio to see this in use.
At a Gamblers Anonymous rally, 120 gamblers attended. 109 men and 11 women were asked whether they gambled at casinos or played the horses. Of the men, 75 played at horse racing and 34 gambled at casinos. 8 women gambled at casinos while 3 bet on horses. Right, now we need to look at all of this information. There's a lot of information there, and we need to actually focus on what information can we use. Right, now the most important bit of information is that there were 120 gamblers at this meeting, or this rally, and that is going to be our total. We have got 120 people altogether. And we need to also then look at the 2 different variables that we've got. We've got men, we've got women, and we've got people that play at the casinos, and we've got people that go to the horses or bet on the horses. When we come to have to fill in our information on our contingency table, we need to actually decide how are we going to design all this information into our table. So we need to have totals. So I'm going to have a total here and a total there. And my 2 different variables. It was either going to be men and woman, and horses and casinos. Now, if I had put these in opposite directions or swapped them around, it would not change my overall table. It would actually make it exactly the same. So obviously the numbers will be in different places, but the actual numbers, if you had to go to the same column and row that matched together to give, for example, horses and women, it would still give you the same number. So that is not really an issue. You need to make sure that you've got your two different variables on different axes or different sides of your table, and you need to make sure that you've got the two different options that match together. You will need to have totals so that you can actually check that you've actually done this correctly. Now we've decided, or we've read, that there was 120 people altogether. So if I've got 120 people altogether, my total over here is going to be 120. I've got 120 people that bet on horses and casinos, and I've also got 120 men and women altogether. Now this is quite a nice example because it actually tells us quite a lot of information. They've told us that there were 109 men and 11 women altogether. So if I go to the total of men and total of women, I will get 100. Check, let's make sure we're getting this right. 109 and 11. 109 and 11. Now, one thing that you need to make sure that when I add these two numbers up, they do add up to the total. If they do not add up to the total, it should ring a bell in your head that you've actually done something wrong. So go back and check. Right, so 109 and 11 adds up to 120, so that's perfect. We know that we've done that part right. And then it said, of the men. Okay, so we're looking at the men's row or column, depending on how we've drawn up our table. In this scenario, you can see that I've got men, and so my two numbers would go into this section over here. So let's go back. Of the men, 75 played at the horse racing and 34 gambled at the casinos. So we've got 75 at the horses and 34 at the casinos. And again, check with your calculator if you need to. If they're horrible numbers, go back and check. And 75 plus 34 should add up to 109. We have 11 women altogether, and they've told us that 8 gambled at the casinos and 3 bet on the horses. So 8 at the casinos and 3 at the horses. So that should actually be adding up to 11, which is perfect. And just go back and check that you've actually filled in the right information in the right slots. Right, once I've got all of this information into my table, I'm now going to add up to make sure that these all add to 120 again. So this should be 78. 75 plus 3 is 78. 34 plus 8 is 42. And if I add those two together, I should get 120 again. So that's my total. Again, if you're not sure, make sure that you are checking on your calculator. There's no marks for making careless mistakes. Right, now that was the easy part. Now you have to answer some questions about this calculations. So you're now going to use your table, so don't make up your answers. You're going to have to use the information that you've already got in your table now to calculate the probability a gambler chosen randomly is female. Now they're talking about gamblers, they're talking about the whole group. So therefore we need to look at, this is the whole group, the whole rally. So what are the chances that a gambler chosen randomly, they always say chosen randomly because if they were in a crowd and you went and just picked one out, what are the chances that they would be female? Okay, so now I need to go look at my table. Probability, as we've said before, is always a fraction, a decimal. So we need to actually then have this as a fraction. So how many of these gamblers at this rally were female? Well, I remember that there was 11. There's 11 women that were at the rally out of the whole group, which is 120 people. So use your table to calculate the probability that a gambler chosen randomly as a female is going to be 11 out of 120. Okay, that means that you've actually got only 11 people that are women out of the whole group of gamblers of 120 people. Right, let's go on to the next question. It says, calculate the probability that a female gambler, chosen at random, gambles at a casino. Now, this is where they start to try and catch you out. They are talking about only the female gamblers. Now, how many female gamblers did we have? We only had 11. So therefore, our denominator has to be 11 because the total number of females is 11. So therefore, if I chose one of those 11 women at random, what are the chances that they gambled at a casino? So let's go look at our table and see how many women gambled at a casino. It was 8 of them. So therefore, 8 out of 11 is my probability that I will get a female gambler that is gambling in a casino.
In grade 10 mathematical literacy, you need to know how to use a tree diagram and a two-way or contingency table, but you won't be asked to draw one up without a problem in mind. Let's look at a problem to demonstrate this. The question asks us what is the probability of rolling a total value of 9 when rolling 2 dice. Look at this dice. How many sides does it have? 1, 2, 3, 4, 5, 6. Like every other dice, this one has 6 sides with dots ranging from 1 to 6 in value on each side. If I roll this dice, I will get a value of between 1 and 6. If I roll 2 dice, I will get a total of between 2 and 12. But we are looking for a total of 9, so let's use a tree diagram to help us. First, we need to know the total possible outcomes when rolling 2 dice. We multiply the 6 possible outcomes on dice 1 by the 6 possible outcomes of dice 2. This gives us the total possible outcomes of 36. To start the tree diagram, let's draw the roll of the first dice. There are 6 different possible outcomes: 1, 2, 3, 4, 5, and 6. Let's think about this for a minute. If the first dice was rolled on a 1, is it possible to make a total of 9 with the second dice? The maximum value that can be rolled on the second dice is 6, which means the highest total you could get would be 7. This means that we don't have to worry about the first branch of the diagram. What about if a 2 is rolled on the first dice? That means that the maximum total we can get with the second roll is 8. So we can cross off the branch with 2 on it. If a 3 is rolled on the first dice, is it possible to make a total of 9 with the second dice? The highest possible roll for the second dice is 6, plus the first throw of 3 gives us a total of 9. So we can draw this branch into the diagram. If the first dice was rolled on a 3, only a roll of 6 with the second dice will make a total of 9. So let's move on to the 4. 4 plus 6 is 10. So the second dice cannot be rolled on a 6 to get the desired outcome. What if we were to roll a 5? 4 plus 5 is equal to 9, and that's the total we want. We can add 5 to the diagram. Are you starting to see a pattern? We don't have to put all the possible outcomes in because we are only looking for a specific answer. Let's speed through the rest of the outcomes. The second dice needs to be rolled on a value of 4. If the first dice was rolled on 5, this will give the desired outcome of a total of 9. If a 6 was rolled on the first dice, we would need a 3 to be rolled on the second dice to get a total of 9. We have explored all the possible ways to make a total of 9 using 2 dice, but we have not drawn the full tree diagram because we did not need to find our answer. There are 4 ways to make a total of 9. This means there is a 4 out of 36 chance of rolling a total of 9 with 2 dice. Just for practice, let's convert this to a percentage by changing it to a decimal first. 4 divided by 36 is 0,1 recurring. Multiply this by 100 to get the answer as a percentage. We get an answer of 11.11%, with the answer rounded off to 2 decimal places. Thank you for joining us, grade 10s. Remember to look at the tasks for this section in the probability tasks video. You will also be able to learn more about probability on our website, www.mindset.co.za/learn. Goodbye.